Hey guys, today we're going to be looking at fluid dynamics, which is all about fluids that are moving. The past couple of class periods, we've looked at fluids that are static, doing hydrostatics with just the pressure and buoyancy. Today we're going to start looking at fluids in motion. Fair warning, I actually did part of this lecture yesterday for the in-person class, but I'm lumping it all together for you guys, so it might get kind of long. My apologies on that. All right, when we're dealing with fluid flow in this class, we're going to make two assumptions. First one is that fluids are incompressible, so their volumes cannot change. And also that we're going to have a steady constant flow, which is laminar flow. There's two types of flow. Laminar is constant. Turbulent is changing. We're not going to be dealing with turbulent in this class because it's all sorts of crazy, just laminar. If you want to know what turbulent versus laminar looks like, there's this lovely picture over here. Laminar flow is the straight sections where everything's smooth and well connected. And then turbulent flow is where it gets all crazy over here. And that deals with some chaos theory and statistics and stuff. So we're just going to stick to the smooth sections and laminar flow. All right, side note is going to be about viscosity. Viscosity is a fluid's resistance to flow, and is represented by the Reynolds number. Viscosity is the resistance. We're not going to quantify it here. It's given by this letter N. N equals the viscosity. It is determined by a thing called the Reynolds number. The Reynolds number is actually really counterintuitive. If there's a large Reynolds number, the viscosity is small. If the Reynolds number is small, the viscosity is large. So that's really weird. But we're not going to be actually using the Reynolds number. It's not within the scope of this class, but it is the parameter upon which viscosity depends. All right, the thing we're looking at first today is the flow rate, which we are going to define as a change in volume divided by change in time. And it's very similar to current, or the idea of current, that you've got a fluid moving past a certain area in a certain time, which lends itself to being a change in volume over a change in time. Basically, amount of water you have flowing through a pipe, the amount of volume that passes over a certain period of time. The first equation we're going to look at today is called the equation of continuity, and we are actually going to derive it real quick based on the principle that a flow rate must be constant throughout a system. So let's look at this system here. I'm going to actually make it a little bit smaller. This system is comprised of two pipes, or two sections of pipe, one with a larger radius, one with a smaller radius. But we know that flow rate must be constant. I'm going to call the large section here section 1 and the small section section 2. So in section 1, we've got a certain volume over time, V1 over time. All right, and then also we have for section 2, we've got change in volume over time, and that's the change in volume in that section. So over the same period of time, if the flow rate is constant, these two things must be equal. So the volume passing through section 1 over a certain period of time equals the volume passing through section 2 over a certain period of time. Now what we're going to derive here is based off of the idea of volume. Now, either the volume is equal to the base area of the pipe, because we're going to assume all these things are like cylindrical or some nice, neat shape that works out well. So it's the area times the distance traveled along the pipe. So here we've got like cross-sectional area. Delta X is how far it travels along the pipe. And that would be the volume that has traveled through the pipe. Delta V equals A delta X. So we're going to plug that in to this equation for the delta V's. Get delta V1 over delta T equals area 1, the area in section 1, times delta X how far it moves, delta x1, divided by delta t. And that equals delta v2 over delta t, which equals a2 delta x2 over delta t. Now, something you might notice here is that this delta x divided by delta t is something familiar to us. That is velocity. Not to be confused here with the v for volume. This is v for velocity. So what this equation boils down to is that the area 1 times the velocity in section 1 of the fluid equals the area times the velocity for section 2. This equation that we've derived here is called the equation of continuity. And as you would expect, this is an inversely proportional relationship. So if you increase the area of the pipe, the velocity of the fluid through the pipe is smaller. And if you decrease it, the velocity is higher, which is like why you put your thumb over a water hose to make it spew water. You decrease that area, which greatly increases the volume. All right, so let's look at an example problem that uses this. This question says a garden hose has an inside diameter of 16 millimeters. The hose can fill a 16-liter bucket in 20 seconds. What is the speed of the water out of the end of the hose? And it also asks what diameter nozzle would cause the water to exit with a speed 4 times greater than the speed inside the hose. RIP, I just realized I forgot to do part B in class. All right, so question A here. What is the speed of the water out of the end of the hose? So let's look at this. We've got our equation of continuity, which says area 1 times velocity 1 equals area 2 times velocity 2. But we also know that this equals the change in volume over change in time, which is constant everywhere in the system. So let's look at our givens. We know that garden hose has an inside diameter of 16 millimeters, which is a radius of 0.08, sorry, not 0.08. It is 0.008 meters. So the area for the hose is pi times 0.008 squared. And we're looking for the speed of the water out of the end of the hose, so that's velocity 1. Now, the other part of the system that we know about is the hose filling the 10-liter bucket in 20 seconds, which is not this A2V2. It is instead this delta V over delta T. So that's what we're going to plug in here. The delta V is 10 liters. We're going to have to convert 10 liters to meters cubed. That's really what kills people on these questions is the conversions. So 10 liters is 10,000 milliliters, which is equal to 10,000 centimeters cubed, which is equal to 10,000 times 0.01 cubed meters cubed, which is 0.01 meters cubed. So that's what we will use as the volume, 0.01 meters cubed divided by time is 20 seconds. And you solve that with a calculator for V1. You do 0.01 over 20 divided by 0.008 squared divided by pi, whatever that is your velocity 1. You can calculate it yourself. So that answers question A. Question B says what diameter nozzle would cause the water to exit with a speed 4 times greater than the speed inside the hose. So if we wanted to change that speed based on our equation of continuity, right now we've got a set velocity 1. If we want velocity 2 to be 4 times velocity 1, I'd do 4 times V1. We could solve for the area 2 equals A1V1 over 4V1. Those cancel. So your area 2 would have to be 1/4 the diameter. So you'd have a diameter there of 4 millimeters. All right, our next topic is Bernoulli's equation and Bernoulli's principle for a fluid flow. which is going to take a little while. So buckle down and bear with me. We were just talking about how fluids will increase in speed or velocity in the narrower sections of a system. However, we did not really examine this intermediate section, the point where the fluid gets squished down, not really squished because it's not compressing, but this transition area between a larger radius to a smaller radius and a lower speed to a higher speed. And you should know from Newton that if something is accelerating, it has to have a force acting upon it. So we're going to examine here the forces acting on a fluid in that little area of transition. So an idea that you should know, and I actually haven't explicitly stated, so I'll state it now, but you should know, is that things move from high pressure to a low pressure. Things go from high pressure to low pressure. And there gets a force exerted in that direction. Because if you've got an object, one end of it's in high pressure, one of it's in lower pressure, there's going to be a larger force acting in the high pressure, or going from high pressure to low pressure, than in the other direction, going from low to high. So things end up getting pushed from high pressures to lower pressures. So if in a system fluid is getting accelerated in a certain direction, it's getting accelerated in the direction of lower pressure. And what we're going to see exists in those sections of tube, like we were just talking about, is that a wider section is going to have a higher pressure than the narrow section, which will have a lower pressure. So there's going to be a force between the high pressure and low pressure regions that accelerates the fluid to that higher velocity. And this area of transition where there's a difference between high and low pressure is called a pressure gradient. And the fluid will accelerate along that pressure gradient. And there is an equation that relates this force and the pressure. If you look at my little diagram over there, you can see that the force going from high to low equals whatever the higher pressure is. We'll say this is the high pressure times the area of the object that's withstanding the high pressure. And then the force that is going from low to high is equal to the low pressure, so pressure low times the area. So your net force is going to be, if we're saying to the right here is positive and to the left is negative, it's going to be the high pressure times the area minus the low pressure times the area. So force equals, sorry, forgot the F there. The sum of forces equals delta P, the change in pressure, times the area. So what you need to know here is that pressure is higher where fluid is moving slower. Pressure is lower where fluid is moving faster. That is the thing called the Bernoulli principle or the Bernoulli effect. And here in a minute, it's going to lend itself to an equation. So one consequence of the Bernoulli effect is that if there is a bump in a fluid where the area around the bump constricts the flow of fluid a little bit, that area right over the hill is going to be an area of lower pressure. So right over the little bump, there's some nice low pressure, which kind of actually sucks up where the bump is, creating a little bit of lift. Now, you probably know that this is where airplanes get their lift, is with the Bernoulli effect. So the region right above the wing constricts those fluids a little bit. It narrows their path, if you will. And right below the wing creates a larger region, which creates a higher pressure zone. So we're going to have a high pressure below the wing with a low pressure above the wing, which generates this lift force. And you can actually see the Bernoulli effect in action here in a second. What you'll need is a strip of paper. It doesn't have to be 1 by 8 inches necessarily. It should be kind of longer. Actually, I guess we could make a really long one to see how good your lung capacity is. But what you do is you take the strip of paper and you put the edge of it right on the bottom of your lip, of your bottom lip, and you blow really hard. Here we see Miss Whiteley in her native environment with her strip of paper. So you put the edge of the paper on your bottom lip and you blow hard. And you can get the paper to just like stick straight out. And this is the Bernoulli principle at work. All right, so Bernoulli's principle lends itself to an equation that we will be using. And we are going to kind of think through / derive this equation, because we all know how much I love derivations. And the way that we do this is by using the conservation of energy. So conservation of energy here is stated in this way. Conservation of energy can be stated in many ways, just means energy isn't lost or gained. This is kinetic plus potential energy. Kinetic plus potential energy is basically all the energy you're going to have. That's the total energy. So a change in energy, which would be the total change in kinetic plus the total change in potential, the change in energy is equal to work, because work is a transfer of energy. So if work is done on the system, it adds energy in. If work is done by the system, energy is lost. And you should know, hopefully, that a system cannot do work on itself, because a system cannot change the total amount of energy in itself. It'd be like you trying to take money out of your savings account and transfer it to your checking account and then saying you have more money. And that's not true. You really don't. So we're going to use this statement of the conservation of energy to look at forces and work and energy inside a fluid system. And from that, we're going to end up deriving Bernoulli's equation. So let's look at this system that we have drawn over here. And in order to look at it, of course, I'm going to make it smaller. So here we have fluid moving from one section of pipe that is larger in diameter to a smaller diameter section, but is also moving uphill over some distance. And we're going to look at kinetic energy, potential energy, and work here. So kinetic energy, we know, is 1/2 mv squared. But here for fluids, we're going to define the mass not as the mass. We're going to define it as rho times v from the density equation, where rho equals m over v. So mass equals rho times v. So that's what we're going to use instead of m here. We're going to say that kinetic energy equals 1/2 rho v squared, where large V is the volume of the fluid that we're looking at, and little v is going to be the velocity. So at a certain point in a system, in a fluid system, the kinetic energy at the point equals 1/2 rho. We're going to put volume as delta V, because it's the change in volume as the fluid is flowing, times little v squared. If it was for point 1, this would be volume 1, velocity 1. If it was at some other point, it'd be volume 2, velocity 2, so on and so forth. Now let's look at potential energy, which is U. We're moving over a height differential, so gravitational potential energy is going to come into play. The gravitational potential energy equals m times g times h. And we're saying mass is rho v. So rho v times g times h. So the potential energy in section 1 would be density of the fluid, sorry, that was a really bad row that I just drew. Density of the fluid times the volume, or the change in the volume at that point, times gravity, times the height, which is going to be our y value. Now, when we're looking at the conservation of energy as stated up here, what we're really looking at is not the exact energy value itself, but rather we're going to look at the change in the energy value. So first, let's look at change in kinetic energy. Say change in kinetic plus change in potential equals W. Let's look at this kinetic part first. So we're going kinetic energy in section 2 minus kinetic energy in section 1 is change in K. Kinetic energy at section 2 is 1/2 rho at section 2 times delta V at section 2 times velocity at section 2 squared minus 1/2 rho delta V1 V1 squared. So just plugging in to our formulas for 1 and 2, subtracting, and that is our kinetic energy term. I'm going to bracket it so we kind of have it sectioned off. Now let's do the same with our potential energy term here. It's got potential energy for 2 minus potential energy for 1. All right, so that's going to be potential energy at 2 is rho delta V2 GH. I'm going to change to be Y. Why would I do this? Well, because the book does it. So this is going to be Y2 minus rho delta V1 GY1. Sorry, it might bug some of you that I wrote those Y's in 2 different fonts. And this equals work. So now really the last thing we have to examine is the work, this W over here. All right, got to move everything down so we can look at just the work. So we know that our favorite definition of work is force times distance, which here we'll call force times delta X, which would be motion through the system. All right, we know that force equals the pressure in that zone times the area times delta X here to make it work. This is the force, that's the distance to make it work. And that comes from the high pressure part of the system. Now the low pressure area also does some work, but it's going to be negative work because it's pushing against the other direction. So that one will be work equals pressure low times the area wherever the pressure is low times delta X. So your total work equals pressure high times area times delta X minus pressure low times area times delta X, which is just equal to the change in pressure times the area times the change in X. And this right here we know to be volume, so you get that the total work equals the change in pressure times the volume. Or well, really that's change in pressure times change in volume, where change in pressure is P1 minus P2, because we're going from high where we started at 1 to low where we ended, which is 2. So we can plug this guy, this term, sorry, that's not a U, that's a V. We can plug this term in for work here, which is going to give us an overall equation of 1/2 rho delta V velocity squared minus 1/2 rho delta V, and these are labeled 1 and 2. There's the kinetic energies plus change in potential rho delta V2 GY2 minus rho delta V1 GY1 equals P1 minus P2 times delta V. This equation is Bernoulli's equation. More often, it is rearranged to look like this. This has all of the energy for one side equal to all of the energy for the other side. All right, so let's see Bernoulli's principle at work here. All right, so up here we have Bernoulli's equation, which we have semi-derived, so now we can use it to solve this example problem, which says water flows through the pipe shown in the figure. The water's speed through the lower pipe is 5 meters per second, and a pressure gauge reads 75 kilopascals. What is the reading of the pressure gauge on the upper pipe? So let's plug and play here. On the second portion, we've got a gauge pressure that we're looking for, so we want to find P2, the pressure in zone 2. The pressure in zone 2 plus 1/2 density, this is water, so density is 1,000, times velocity through that area squared. We don't actually know that velocity. We know the velocity in the lower pipe is 5 meters per second, but we don't know the velocity in this other section. So we can find that using equation of continuity, which says area velocity equals area velocity. We can see that area number 1 here has a radius of 6 centimeters. I'm sorry, that's a diameter of 6 centimeters, so it's a radius of 3. So area would be 0.03 squared times pi, and the velocity is 5 meters per second times 5 equals area over here, which is a diameter of 2 centimeters, so 0.02 squared pi times v, which will give you a velocity over here of 11.25. All right, so that's V2. So we'll do 11.25 squared there. Plus rho, density of water, is 1,000 again. Times gravity, 9.8. Times Y2. Y2 is 2 meters. All right, and then this equals the pressure at 1, which is 75 kilopascals. Now, this is a gauge pressure because this is a gauge reading. So we need to add the 1 atmospheric pressure to it, which is 1 times 10 to the 5th plus 75. Now, what you could tell is that if we put gauge pressure there like that, when we read pressure over here and turn it back to gauge, this 1 times 10 to the 5th is just going to cancel out and go away. But it's still important to know that it's actually a pressure that is included there. All right, so that is 1 times 10 to the 5th plus 75 for the pressure down there in section 1, plus, I'm going to have to make this whole thing shift. All right. Plus 1/2 rho is still 1,000 times V1 squared. So V1 is 5 squared plus 1,000, still running out of room. 1,000 times 9.81, I guess, times, I'll put the term over here for Y1. Y1 is going to be at what we'll call 0. So this term will go away. All right. So you can use that to solve for P2. I'm not actually going to do it out numerically here because I don't feel like typing it into a calculator. But that would be how you'd find P2. However, it is gauge pressure, so you'd have to do whatever pressure you get here minus 1 times 10 to the 5th. So you'll see this is what you're actually looking for is P2 minus 1 times 10 to the 5th. So equals pressure to gauge. So pressure 2 would be pressure to gauge plus 1 times 10 to the 5th, which if you substitute in there, you'll see that you could just take this 1 times 10 to the 5th and subtract it off each side and not even deal with it. So these pressures you could use straight up the gauge pressure and be fine, and that way you don't have to keep up with quite as many digits. All right, guys, that is Bernoulli's equation, which is an extensive amount of variables and thinking, but really it's just conservation of energy and work. So if you have any questions, please let me know.